All right, let's get right into it. If you've ever set foot in any kind of industrial plant, I'm talking power stations, chemical plants, food processing, you name it, you've been surrounded by the 4 to 20 milliamp signal. It is, without a doubt, the universal language for almost every process measurement out there. It's the invisible current that makes sure everything just works. But here's the kicker. It's a question that trips up a ton of people, even seasoned engineers in job interviews. If you're measuring something from its lowest possible point, why on earth does the signal start at 4 milliamps and not a nice round logical 0? Well, that's exactly the mystery we're going to unravel today.
To get to the bottom of that, we first have to really wrap our heads around what this signal is. You can think of it as the language that machines use to talk to each other. A way for a sensor way out in the field to have a conversation with the main control system, the brains of the whole operation.
At its heart, what we're talking about is an analog current loop. It's a ridiculously reliable and robust way for an instrument, like a temperature or pressure sensor, to report what it's seeing back to a control system, like a PLC or a DCS. And it does all this using a simple, steady stream of electrical current. And that journey is almost always the same. So step 1, a sensor measures a physical thing, pressure, flow, level, whatever. Step 2, a transmitter takes that reading and translates it into an electrical current somewhere between 4 and 20 milliamps. That signal then travels down a wire, sometimes for hundreds of meters, all the way to the control system, which then reads that current and decides what to do about it.
Now, the real beauty of this system is its perfect, predictable, linear scale. So let's say you've got a pressure transmitter that measures from 0 to 10 bar. When the pressure is 0, it sends out exactly 4 milliamps. If the pressure climbs to the halfway point, 5 bar, you guessed it. You get 12 milliamps, right in the middle of the signal range. And when it's maxed out at 10 bar, it sends the full 20 milliamps. Simple, direct, and there's no guesswork.
Okay, so now we get to the core of it. We have the background. Let's solve this 0 problem and really understand the genius behind starting at 4 milliamps instead of 0.
And the answer. The entire reason boils down to one brilliant, elegant concept. It's called live zero. And trust me, this isn't just some random technical detail, it's a critical safety and diagnostic feature that's baked right into the standard. So let's do a little thought experiment. Just imagine for a second that the standard was 0 to 20 milliamps. Now, if your control system suddenly sees a reading of 0 milliamps, what does that mean? Does it mean the tank you're measuring is completely empty? Or did a forklift just run over your cable and break the wire? You'd have absolutely no idea which it is. And that ambiguity, well, it's not just confusing, it's dangerous. But in our real world, with the 4 to 20 standard, 4 milliamps clearly and cleanly means one thing, the lowest value. And this is key. It also confirms the system is powered on and working perfectly. So, this is the most crucial point to remember. In a 4 to 20 milliamp system, a reading of 0 can only mean one thing, a fault. Something is broken. The wire's been cut, the power's out, the transmitter's failed, there's no ambiguity whatsoever. The control system knows instantly that something is seriously wrong, and it can trigger an alarm, preventing a major problem or a dangerous safety incident. So to put it all in a nutshell, this live zero gives you immediate, built-in diagnostics. It lets the system tell the difference between a normal, everyday low reading and a critical system failure that needs someone to look at it right now. It is just an incredibly clever solution to a very serious problem. But, this amazing fault detection is just one of the reasons this standard has been on top for decades. It was also engineered from the ground up to be tough as nails, especially for the kind of harsh, noisy environments you find in industry.
I mean, think about the floor of a huge factory. If you're using a voltage signal, it can get weaker and weaker over a long cable run. But a current signal? It stays perfectly consistent. On top of that, it's way more resistant to all the electrical noise, the electromagnetic interference, coming off of giant motors and variable frequency drives. All that dirty power just doesn't mess with it.
So we know why it's the standard, but how does it all physically get wired up and powered? Well, the practical side of this is just as smart as the theory. The whole circuit, that's the power supply, the transmitter out in the field, and the input on the controller, they all form one single simple series circuit. And we call this a current loop. In almost every case, this whole loop is powered by a standard 24-volt DC power supply. Now you're going to run into a couple of different ways these things are wired. By far the most common type is the 2-wire transmitter. It's super efficient because it actually sips its power directly from that 4 to 20 milliamp signal. So the same 2 little wires carry both the power to the device and the signal back from it. Now, if you have a more complex device that's power hungry, you'll see a 4-wire setup, which just means it has its own separate power supply. And yeah, that two-wire setup is absolutely the king of the castle. If you walk into any large plant, the vast majority of instruments you see are going to be these simple, elegant two-wired devices. It just makes everything, from wiring to troubleshooting, so much more standardized and straightforward.
So at this point, you're probably thinking, okay, I get it. It's a clever, old-school analog signal, right? Well, what if I told you this old dog has learned a very cool new trick? What if I told you it can also speak digital? And it can, thanks to something called the HART protocol. This is a truly brilliant piece of engineering that piggybacks a low-level digital signal right on top of our trusty analog current. It's like sending a secret text message along with a phone call. It doesn't interfere with the main measurement at all, but it lets a technician talk directly to the instrument, maybe from a laptop in the control room. You can run diagnostics, change its settings, all without ever having to go out into the field. It's this kind of adaptability that keeps a decades-old standard on top.
So, when you pull it all together, it becomes pretty clear that this is not just some old, outdated way of doing things. It truly is the fundamental backbone of modern industrial automation.
And that, right there, is why this all matters to you. It doesn't matter if you're configuring a PLC, trying to figure out why a sensor is acting up, or designing a brand new system from scratch. A deep, solid understanding of the 4 to 20 milliamp loop is, frankly, non-negotiable. It's one of the first and most important steps to really mastering this field.
You know, for all the talk about fancy wireless technologies and new digital field buses, this simple, tough, and brilliant analog standard is still the undisputed workhorse of industry. Why? Because it just works, every time. Which really leaves us with one final big question. After all these decades of flawless service, what on earth is it going to take to finally unseat the king?